such kind of phenomenon really depends on the time, right? 10 years before, we can use this mathematical modeling, but 10 years, 20 years later, no longer we cannot apply, I think, because this phenomenon should have a bit more affected from some kind of infection, right, from the time. Okay, so then we need to upgrade. We need to upgrade mathematical model along the time. So then today I really want to talk about if we upgrade the model, mathematical model, and then how much this mathematical model affect such kind of changing. So then that is I want to focus on today's talk. So then to understand just one example of such kind of upgrading, and then how much we got affection from such kind of changing or upgrading. All right. So first of all, okay. So this is some kind of connection of the biophysics to the random walking random environment. The original motivation is just the DNA unzipping. When DNA try to replicate their self, and then this is some kind of the DNA chain, and then this green triangle is the DNA helicase, and then we just assume this DNA helicase is a random walk, means go forward, or sometimes here this chain has a winding force, so then going back. Not going back, just a speed down. So then this motion is going to the right, we call right transient, but the speed is randomly changing. In this sense, we say random walk. And this A, T, C, Z, so this is a basis, these are bases, and then this is some kind of assumption, this is a random environment. This is not a random, I guess, because this is a DNA. But we just make a random environment. This is our assumption, but not so real. In this case, and in this model itself is really interesting, but unfortunately, this is not real model. Okay, so then we have to say this is toy model. This is some kind of the motivation of the random walking random environment. So random walker and the random environment. But the AT connection is a bit stronger than CZ connection. So then randomly, this DNA helicase hit the stronger connection or weaker connection. So then it depends on the speed. Speed of the DNA helicase is depending on the also random environment. Okay. Okay. So first of all, so we start from just a random walk. So then today we don't have enough time. So then I just see this one. If you are the position X, the random walk means jump to the positive, or means we say jump to the right, is probability P. P is in between 0 and 1. And the jump to the left is 1 minus P. This is a really easy understanding of the random walk. Okay, so we just consider such kind of the model. And then after n step, where is the random walker? So this means Sn. And the mathematician, we really are interested in such kind of the formula and the theorems. And these are already proven in the random walk theory. And this Sn is written by the first jump, second jump, so this is the type of capital X2, so second jump, and the Xn, the nth jump. And every jump is independently and with the same probability distribution, right? And then under such kind of situation, and also with some moment condition, we can prove law of large numbers. Sn divided by n is converged to the expectation of this x. And the central limit theorem, right, going to the Gaussian, and the large deviation principle, recall this random walk satisfy the large deviation principle means this convergence speed is exponentially fast, right? If this convergence speed is exponentially fast, we just say, oh, this random walk satisfies the large deviation principle. So we really care about these kind of the topics, okay? And also this already we have this one. So this is a basic, some kind of basic of my talk. And then we have a question. if we introduce the random environment, this result, how much affected from the random environment, right? So then before showing the result, I just introduce some definition of the random environment. So you just see this one. So previously, random walk is here. Just probability p jump to the x plus 1, jump to the x minus 1 is 1 minus p, but here we just put omega x. P depending on the position x. In this sense, we say space inhomogeneous and random sense. Okay? Random environment is a set of jump probabilities, but these jump probabilities depending on the place. Okay? Under such kind of the situation, we just construct such kind of the jump process. And then we just try to think about the low Raj numbers, CLT, and the Raj deviation principle, how much affected from such kind of the environment. The first one, so this is a recurrence, and this one is right transients. We have these two phases. The first phase is you just stay. Yesterday, so I had a big drink with my friend. Just I drank a lot of beers, and then if you got drunken, so your walking looks like a random walk. And then this recurrence implies, can you go back to your home or not? And the situation recurrence is for sure you can come back to original place again and again. But the right transience is you go to infinity, means you cannot come back to your home forever. So basically, if you consider this one, 1 minus omega x and divide by omega x, this is a ratio, jump to the left and jump to the right. And if we consider this is bigger than 1 or smaller than 1, so you can get some tendency of the random walker. Because if this is bigger than 1, so then the omega x is smaller than 1 minus omega x, means goes to left, right? Such kind of tendency we can guess. But unfortunately, this result is, we don't have to care about the rho. No, we have to care about log rho. This is the first affection from this upgrade. Basically, random walk case, we only care about this rho x. That should be fine. We can understand going to the right, going to the left, or stay some place. We can understand. But if we introduce random environment, we have to be careful, rho. Okay, that is the first upgrading part. And next result is about the low Raj numbers. Basically here, expectation of rho bigger than 1 or smaller than 1. So then we have two speeds. One is 0, and another one is positive speed. So then we just say 0 speed case and positive speed case. Okay? But this is a bit strange because people say right transients means going to the right, but the speed is 0. A bit contradictory words. Unfortunately, we say this is positive speed, but the meaning is Vn behaves like V mu times n. This means ballistic speed or linear speed, we just say. But in this case, Vn divided by n is equal to 0. This just implies this random walker Zn is not the linear speed, means sublinear speed. Still, random walker has a speed, but it's slower than linear. And why such kind of speed down effect occurs? The reason is trapping effect, we call. And this trapping effect is really typical in random environment case. So then this trapping effect causes such kind of speed down or some other anomalous behavior. The first, this speed down, this is positive, but this is 0. Such kind of speed down comes from this trapping effect. And why such a trapping effect occurs? So we just consider, our assumption was rho is strictly smaller than 0, and the expectation rho is positive. And rho bigger than 1 means tends to the left. Because the rho is jump to the left, jump to the right, such kind of a ratio. So this condition gives us the random walker tends to the left, means many backward jumps. But this rho is strictly smaller than 0. gives us the right transient. So then this random walker wants to go to the right. Random walker wants to go to the right, but we have many backward jumps. Means going to the right, going to this direction, but this condition tells you have to go back a lot of times. Means you have to stay someplace. This gives us the slow down effect. Okay. All right. So this part is a bit I want to skip, and then this one. So next is we need to think about the central limit theorem. Because we already understand the Lagrange numbers and how much the random environment affect to the Lagrange numbers. But here, this one is a CLT. So in this case, zero speed and positive speed, we just care about the S is equal to 1. This is a threshold. But for CLT, the threshold becomes S is equal to 2. This is a result. And if we have such kind of speed down effect, gives us the no longer Gaussian, stable rho. Such kind of the result is also affected from the random environment. Because if we don't have any random environment, everything is Gaussian. But due to the random environment, we can find such kind of stable situation. Okay, so this part is also the affection from the environment. And next is the Rage derivation principle. And especially in this Rage derivation principle, we really care about this rate function. This gives us how fast this probability that the n divided by n goes to this d mu, right? Asymptotic speed we have. But this convergence, how fast this rate function I gives us. And the recurrent and the zero speed case is strictly convexity. We have a strict convex, but unfortunately, positive speed case, we have such kind of the flat piece. In this flat piece, no longer this power is not n, and also this power n is no longer we don't have. This n becomes log n or log n squared, unfortunately. So then this part is also the random environment effect. If we don't have any random environment, rate function should be like this. Now, unfortunately, we have some speed down effect or random environment effect. We have such kind of the situation we have. So now we understand. Okay, if we assume random walk with random environment, then we have such kind of the modification of the result of the random environment and random walk. Okay, and then my main job was when I was in the Netherlands before Taiwan. So this is the main job in the Netherlands. So again, we put some other conditions. Means cooling means dynamics. We just assume the dynamics in the random environment. So we consider random walk, and then we assume random environment, and next dynamics. So I modify twice. So then this kind of this is omega n. So also depending on the time. So if we assume such kind of dynamics, what kind of the affection gives us? This is the next question. The answer is actually just this is some kind of the schematic picture of the random walking cooling random environment. Looks like a patchwork of classical random environments. Because first time 0, we choose the random environment omega 1, and we define deterministic time sequence. This time sequence we call dynamics. And this tau 1, we re-choose another random environment omega 2. And continue the random walk. And then at time 2, again we re-choose another random environment omega 3. And then we continue, right? So then this part, the time span T1, we have the classical random environment. Only this time span T2, also classical random environment. But we just patchwork omega 1 and omega 2. This is our model now. And if we consider such kind of modification, what kind of the result we got? So the first one is strong Lagrange numbers and LDD. fortunately or unfortunately, I'm not sure, no change from the classical model. So then this is sometimes good, sometimes bad. In mathematically, not so interesting, right? But from the view of the natural science or social science, this is sometimes meaningful. And next is fluctuation. So this is some kind of very good result. If we consider the dynamics, so then limiting distribution is something like this is a classical distribution, and here is Gaussian. So we have some kind of a mixture of the Gaussian with classical model. And this lambda, A lambda, is some kind of the balance of the how to mix these two parts, depending on the dynamics. And if you choose some kind of the Tk is almost a polynomial and the constant speed, this is some kind of determine the dynamics. You can have the CLT. This means homogenization occurs. And then this polynomial exponential speed, still we can find some kind of Gaussian, means also homogenization, some small homogenization occurs. But if Tk is very, very big, so then we just care about the normal or classical situation. But this is not so tough to imagine. The reason is our picture. Because if Tn, this is like a Tn becomes bigger and bigger, and this is not so big. So then of course this is dominant. And this dominant part is classical model. So then we can see the classical model. That's all, right? So then now we understand, okay, first we have the random walk, and we update the random environment. And then we got some affection. And again, we modify the model, random walking random environment with some dynamics. Then we can understand some other effects from the dynamics here. Okay? So this is the last topic of my talk, and then this is a difference. So then now we understand, okay, if we upgrade the model, we have to consider how much this modification affect the result. That is what I want to, or what I'm interested in. Okay, so thank you very much for listening to me. So 感谢大家的聆听。